Planck Institute for Extraterrestrial Physics. And well, Andrea is a well-known, recognized expert on black hole all kind of fashion, from theoretical and observational point of view. But today, has the mission project scientist, he will talk us about the new X-ray mission in Rosita, and will tell us new exciting results about this first months flying. And at the end of the session, there will be the question, at the end of the talk, there will be the question session. So please, if you have any question, just let me know in the chat, so I will give you the floor. But now I think we could start, and I will leave the stage to Andrea. And thanks.
Thank you. Thank you all for being there. I don't see you now, but I'm sure there are many friendly, familiar faces there. And thanks, Alessandra, for inviting me. So today I'm going to tell you about eRosita on SRG, and the outline of my talk is simple. I will start with just a basic recap of the scientific motivation for the mission, some historical notes and technical characteristics. And then in the second part of my talk, I will present some reports on the status of the mission. Maybe I will tell you some technical problems we've had, and a description of how we go around in operating the mission and solving our problems, and then hopefully finish with some nice pictures and highlights from our early science program, including an outlook of the All Sky survey that we are doing right now. But of course, as you can imagine, given these very early times, this will be more a qualitative description rather than an in-depth series of science results, as we are all working very hard on this first data. Okay, so eRosita has been designed, as I will tell you, as a survey instrument, and surveys can do many things in astronomy. You know, they gather large amounts of data that you can use to find rare objects, to unveil hidden trends, or just to do population studies, out of which you learn about the astrophysics of stars and galaxies. But of course, one of the things that surveys do is also give a map of your neighborhoods, a map of your environment. This is a very sketchy, simple plot from one of the early spectroscopic surveys from the 90s. Is a CFA spectroscopic surveys that were instrumental to reveal the filamentary nature of the large-scale structure, which I think is a very influential discovery. This is another now whole sky spectroscopic surveys. This is a 2-mass redshift surveys. Here galaxies, nearby big galaxies, are color-coded by their velocity. And this is an interesting data set because you have position and velocity information over the entire celestial sphere about the very nearby universe. And so you can use this to reconstruct the dynamics of the underlying mass distribution. So you can actually put this into a computer simulation, and you can do so-called constrained hydro simulations, constrained by the actual observed position of galaxies. So you can have a simulated universe in which known systems like Virgo, Perseus are placed in the right position in the sky. And in this particular image I'm showing, because this is now a computer simulation, you can, instead of looking at the visual universe, you can switch on your X-ray eyes and see how the sky would look like if you were able to observe the hot gas in the filaments and the clusters. And if you want, one of the motivation for building eRosita, the eRosita instrument, was to turn this computer picture into reality. Of course, this is nice to say so, but funding agencies probably need also some more hard-wired motivations. And the main one for us was to use these clusters and large-scale structure tracers as a cosmology tool. This can be done in X-rays because the typical patch of the extragalactic sky that here on the bottom left you see simulated mainly contain quasars, supermassive black holes, and diffuse emission from clusters or groups, because stars themselves do not emit strongly in X-rays. So your X-ray sky is pretty free from contaminants from stellar emission, and instead highlights this hot side of the universe. And of course, the other element is once you measure and you're able to observe these clusters of galaxies, not just in the local universe, as I was showing you in the plot before, but also at high redshift, then you know that these are exponentially sensitive tracers of the underlying cosmological parameter. And this is very simply illustrated by this plot on the top right from an influential review from Piero Rosati, Norman, and Borgani in 2002 that shows the number density, cumulative number density of clusters. So number of clusters above a certain halo mass as a function of redshift, all normalized to the redshift 0 numbers. And this tells you, these different curves tells you the difference in the number density that you predict with different cosmological parameters. Of course, some of these are clearly now not considered valuable anymore, but this is a logarithmic scale on the y-axis. So if you are able to accurately measure and count objects as a function of mass and redshift, you have a very powerful tool to do cosmology. And this, of course, has been already exploited in astronomy since maybe 20 years, 30 years, by the time Rosat assembled the first sizable sample of hundreds of clusters. So that was the main motivation, and quantitatively a paper by Hyman et al. In 2005 put the goal post of the order of 100,000 clusters that you would need in order to beat down your statistical errors to a level that you get a very stringent constraint on fundamental cosmological parameter of the dark energy family of models. So this requires, of course, very large effective areas, given what we know about the cluster population, and sensitivity in the soft X-ray range between a fraction of a keV and a few keV, where the hot intracluster medium mostly shines. So that have driven the design of eROSITA instrument. The original proposal to the German Space Agency, DLR, was led by Gunther Hasinger in 2006, and approved in 2007. And in 2008, an agreement was found between the German Space Agency and the Russian Space Agency, Roscosmos, to make eROSITA the key instrument on the spectrum Röntgen Gamma mission dedicated to survey the X-ray sky. And in 2008, essentially, mission was consolidated and adopted, adding to eROSITA a second hard X-ray telescope called ALTO-XC, and the mission profile in L2 was also approved. And this will end up being the first Russian mission in L2 ever. On the Russian side, the spectrum Röntgen Gamma name has an even longer history than eROSITA has. There was an old Spectrum X that maybe some of you in the audience will remember from the late 80s. It was a large international cooperation that, however, did not serve mainly to study X-rays with a number of different instruments, none of them resembling the actual ones, but that mission did not survive the funding crisis of the Russian space science after the collapse of the Soviet Union, and it was revived in the year 2000s. And so it was finally, as I said, approved in 2008, and it became Spectrum Röntgen Gamma, or SRG, under the joint leadership of Rashid Sriniaev and Peter Predel in Germany. About eROSITA itself, as I said, it has been entirely built at MPE in Germany by a consortium of few institutes which received funding from our National Space Agency and by Max Planck Society mainly. And you see them on the left with, of course, a number of important industrial partners, out of which I really want to mention Medialario, from LECO, that build the mirrors. So one of the key technology aspect of the mission. And one particular aspect of the project that I want to stress here is the how large the fraction of the work that was carried out in the consortium was on the shoulder of MPE. Peter Predel from MPE is the PI of the mission. I am the project scientist, and Paul Nandra, the director of the INEG group, share the main mission level management aspects. But the entire institute have contributed heavily from not just at the science lead or project management side, but on the instrument design, the manufacturing of most of the parts. More than 70% of the flying parts were actually manufactured in our labs. And we did all the integration of the telescope and all the testing. And now we are very busy with parts of the operation, as I will tell you, and we are doing all the data handling, processing, and archiving at MPE with support from other institute in Germany mentioned here. So it was, of course, as you can imagine, quite a big investment of resources and men and people, men and women, over many years from a single institute, which is not quite exceptional for a space project of this size. So it took about 11 years to go from mission adoption to launch, maybe twice as many years as optimistically predicted at the beginning, but here we are. Last July in Baikonur, it was a cloudless, hot day, 42 degrees in the shade, and we launched. But let me pause here and make a step back and tell you actually what did we launch? How do the hardware that we built look like? This is now a picture taken a few days before launch in Baikonur during the final integration. And here you see all the elements of SRG. The two instruments, the two telescopes are on the right. Rosita is the bigger one on top. And Arctic-C is this slender black cylinder on the bottom. It's a smaller telescope that operates in hard X-ray. I will tell you something more about that in a minute. And the two instruments point in the same direction of the sky. They are coaxial, and they are mounted on the spacecraft navigator, is called, built by Lavochkin, a Russian Roscosmos subsidiary. Here you see the solar panels, and the spacecraft plus the instruments are here mounted on the upper stage, Block DM, that brought the telescope into its final orbit. So one word about the Arctic-C telescope, mainly because this is a PI instrument of which I personally don't have access to the data, but to let you have an idea of the performance, it's a focusing telescope. It's the only the second one after NuSTAR in orbit in this hard X-ray regime. It operates mainly between 4, maybe not 5, but 4 and 30 kV. Here you see the effective area on axis of Arctic-C in red compared to NuSTAR in green. So it's a factor of a few smaller than NuSTAR, especially at high energies. But around 6 kV, it's a significant effective area with a very good spatial resolution of the order of probably 50 arcsecond is the number I get from in-orbit calibration, and the field of view of 34 arcminutes. They have cadmium telluride detectors, which have energy resolution of order 10% at 14 kV, and the time resolution of 1 millisecond. So it's definitely, for this energy range, a quite powerful telescope. But okay, let me focus now more on Rosita, the bigger of the two sister telescopes. Here you see a couple of pictures taken in our integration lab at MPE. The one on the left shows the entrance side with the 7 mirrors. So Rosita is actually an array of 7 identical mirror telescopes and cameras. The mirrors are shown on the left. They are quite compact. They have small focal length compared to, say, XMM of only 1.6 meters, but a large field of view of 1 degree diameter. And the small focal length, of course, is because we are mainly interested in soft X-rays rather than hard X-rays, for the reason I told you before. The mirror themselves are very similar characteristic to the XMM ones. They have on-axis alpha energy width of, they would deliver on axis alpha energy width of about 16 arcseconds. We have slightly defocused them to 18 arcseconds because what we are interested in is the field of view average that is relevant for survey mode observations. And this is between 25 and 26 arcseconds. That would then deliver as I will tell you later, source location accuracy of 3 to 5 arcsecond. Here, the pre-launch estimate were a bit pessimistic, especially because Spacecraft is delivering very good pointing stability. In front of the mirror that you actually see here with the spiders, there are X-ray baffles that have been manufactured at MP and aligned to the mirror to micron precision that are there to avoid single reflections, which essentially can cause stray light to hit your detectors and would then end up being a background that reduce your sensitivity to low surface brightness objects. On the right, you see the focal planes. We have 7 identical cameras, and these cameras are an evolution of the very powerful and performing PN CCD that has been flying on XMM for more than 20 years. Compared to the PN XMM cameras, we have frame source, so we have no out-of-time events. There are no chip gaps. The entire 1 degree field of view is exposed in the cameras, and it's sensitive to photons. We have very good detector uniformity, little temperature dependence, and a spectral resolution, which is maybe a factor of almost 2, maybe 1.8 better than XMM PN. So by all standards, these are probably the best CCDs for X-ray astronomy that have ever been flown to space. So the mirror camera contribution give you a field of view effective area, which is very large. I think this is an important message I'm telling my colleagues all the time. This is now the field of view average effective area as a function of energy. So between, let's say, 0.3 and 2 keV, Rosetta 7 telescope combined in red is essentially as big as XMM Newton. And his blue curve is PN plus MOS. Of course, because of our short focal length at high energy, we have a much smaller effective area. But of course, the other key elements is the large field of view. So once you multiply your effective area times the field of view, you get the grasp or survey speed metric. And so the grasp of Rosetta is a factor of 5-6 larger than XMM Newton. So it's a factor of 5-6 bigger survey machine, if you want. And compared to Chandra at 1 keV, this is, we are talking almost a factor of 100 gain in survey speed. And this is a simple pictorial illustration of this, the field of view of Rosetta compared to the Newton-Chandra field of view. There is one other characteristic that you hope you will appreciate when I will show some of the image. It's not just that we have a large field of view, we also have implemented a mode of observation which allows us to design rectangular fields of any given size from a couple of square degrees up to maybe 150 square degrees by doing these raster scan operations. And this delivers very good uniform exposure over arbitrary large areas up to 100 square degrees. And you can, of course, change your scanning speed, and by adjusting that, you can adjust the depth of your images. But this is what allows Rosetta to deliver very nice looking images over very large areas. Okay, now a movie that I hope you will show of the status of the way we operate the mission during the surveys. And this is doing in scanning, okay? We are now a few months into the Old Sky survey, and this is done by letting the telescope continuously rotate and do great circles in the sky. It takes about 4 hours to do a full great circles. It runs quite slow. It rotates much slower than Planck, for example. And all the great circles intersect at the ecliptic poles. And because the field of view is 1 degree and the spacecraft is around L2, and the L2 point, as you can see here, moves around the sun in 6 months by 1 degree per day. So in exactly 6 months, we can cover the Old Sky. And the plan is to do that for 4 years uninterrupted, so that we will have 8 independent scans of the Old Sky. And this will be then followed by pointed observation. We have funding for 2.5 years after the end of the Old Sky survey, and there will be open time for the community to apply to use Rosetta. So the survey metrics are shown here. Let's focus on the plot on the left that shows the typical survey quality. So this is the area that you cover on the x-axis in the sky in degrees, square degrees, versus your flux limit or sensitivity. Here on the top right, you have an Old Sky survey, and this is the only existing one at Soft X-NG, the Rosat All Sky Survey here, with a few times 10 to minus 13 sensitivity limit. So eROSITA first All Sky Survey, the one we are completing now, it's already a factor of a few more sensitive than Rosat. And when you combine and you stack all the 8 surveys, you get this red line that is maybe a factor of 30 deeper than Rosat over the All Sky. And in the ecliptic pole, of course, this is deeper because we get more exposure there. And that becomes comparable with medium-sized depth XMM surveys. Of course, we are definitely in a different regime as well compared to pencil beam surveys like the Chandra Deep Fields, which are very small area but much deeper. And I said that the main motivation was cosmology, and this is just one slide illustration of how our instrument design ties in with that. The key element, of course, is to be able, by looking at your X-ray image, not just to have enough photons to detect clusters, but to be able to distinguish the clusters from the point source. Okay, and this plot shows as a function of redshift the extent in the sky in arc minutes of the R500 radius, which is the typical use radius that mark the location in the cluster where the intercluster medium density is 500 times the critical density of the universe. And so this red line marks 1 arc minute. I told you that we have a half energy width of 26 arc second that correspond to full width of a maximum of about 10 arc second. And these green lines are the tracks for dark matter halos of 10 to the 13 solar masses, 10 to the 14 solar masses, 10 to the 15 solar masses. And these blue points are Rosat and XMM really observed clusters. So you can immediately recognize that with our PSF we can resolve, let's say, cluster larger than 10 to the 14 or a few times 10 to the 14 to redshift 1. Then the sensitivity, you can fold in your sensitivity, looking at how many clusters there are per unit area in the sky, and then the prediction comes that we should be able to detect more than 100,000 clusters, that the numbers we needed for cosmology constraint. And in fact, it turns out that essentially we will be able to detect not just, so essentially all cluster more massive than 2 times 10 to the 14 solar masses that lie on our past light cone. And because we are able to resolve them, at least the vast majority of them between redshift 0 and 1, then we have access to different measure of the hydrodynamical quantities that we can then use to infer the gas mass, which is the main observable needed to do cosmological constraint. But I don't delve into many details about that. Maybe we can discuss those later. But this is just an illustrative plot that now from a published paper by Jean Comparat last year that have used the latest, just pre-launched instrument characteristic, and they've built very large, sophisticated numerical simulations, starting from n-body simulation with painting on top of this n-body simulation galaxies and clusters using abundance matching, rescaling observed clusters by their mass and redshift, and essentially then generated a fake model of the X-ray sky, and then we passed that through a 6D simulator, so a simulator that simulates eROSITA observations. And these wedges illustrate with red and blue dots the location in the 2D distance position space of the object eROSITA will detect in the simulations after the end of the all-sky surveys, so assuming realistic flux limit and so on. And so you can immediately see that once you can place this object in this 3D space, they can be used directly to trace large-scale structure in a unique way, which is complementary to using, let's say, normal inactive galaxies. So that's the main, goal, long-term goal. But of course, that's obvious, almost trivial to say that once you open up a couple of orders of magnitude in your parameter space and you do that over the whole sky, you're bound to have a large legacy sample that can keep many scientists busy. So beyond the detection of 100,000 clusters, we expect a few millions AGN, given what we know of the X-ray luminosity function of AGN. Their typical redshift Their median redshift will be around redshift 1, and medium luminosity in X-ray around 10 to the 44. So an interesting subset of the entire AGN population will be probed by Rosita. But of course, we will be going over the Milky Way, and in the process detecting compact objects, population of neutron stars and black holes, plus a very large number. We are now estimating a few hundred, maybe 700,000 or so, maybe up to 1 million stars. Okay, with probably more sensitive to the young, magnetically actively fast rotating stars, but all stars at some level emit X-rays, and so we will be revolutionizing, I think, hot star and magnetic star population studies. But our spectral capabilities of our cameras also will be very important to study the diffuse X-ray emission, looking, for example, at the hot ISM in the Milky Way and the hot ISM of nearby galaxies and groups. Plus our scanning mode of going over the same position of the sky a few times in a day and then again over a few months period will be very interesting to study transients. The dynamical X-ray sky is also something poorly explored at these sensitivities, including, we hope, hundreds or thousands of tidal disruption events. And then, of course, if one is ready, this will probably be a treasure trove of phenomena we don't even expect or we don't even know exist. So that's what we built and why we did it. A few words now about how people get access to working with eROSITA. eROSITA is a PI instrument, and the scientific exploitation of the data, as I'm sure many of you would know, is shared between the main partners, which are the Russian and the German team. And we have now decided to share this by dividing 2 surveys in West and East galactic coordinates, over which each team has scientific exploitation rights. The German side of the data sets, of our half of the survey, will be made public after 2 years, and we are planning 3 releases of incremental depth. So the first Whole Sky survey will be released in 2 years from now, more or less, and then after 2 years, and then after 2 years, we'll be releasing deeper and deeper half sky survey data. If people want to get access to the proprietary data before these releases, then you can only do so by collaborating with the consortia, either the German or the Russian consortium. In Germany, we are organized by different working groups. We have about 150 members of the science community and a couple dozen external collaborators. Here, there is a list of the working groups. I think if you go online on the www.mpg Rosita website, you will find the actual name of the contact points. And we have a quite busy program of collaboration, not just individuals that bring to us, access to telescope time or different skills and resources, but also large survey teams that for which we have strong synergies in multi-wavelength astronomy. And there is a list here on the bottom. Okay, I think now we can go back to that day in July in Baikonur, ready to launch, in fact, launching eROSITA. The launch itself was executed by a Proton rocket flawlessly. The launch was, in fact, perfect. Here you see a brief diagram. After the first 2 burns, the spacecraft and the upper stage were placed into a low Earth staging orbit, parking orbit. And then after just 1 orbit, 1 hour and a half after launch, the upper stage ignited and placed the spacecraft into this very high elliptic orbit towards L2. And in fact, about 2 hours after launch, almost immediately after spacecraft separation, we opened our solar panels and we got telemetry within minutes. That was already a very good sign. So this is now a plot of the current orbit that has been delivered. It's a very large halo orbit, okay? It's not at L2, but in this very large halo orbit, which has a major axis almost as large as the distance between L2 and the Earth, which is 1.5 million kilometers. And K1, K2, and K3 represent the 3 major orbit correction maneuver that the spacecraft had to do in order to be inserted in the orbit. So the final one was in October 2019, on 21st of October. That is the time where we consider that we reached our desired orbit. And these blue points here show the position of the spacecraft in April 16, so almost a month ago, when the first circulation around L2 was completed. And so we are now already in our second orbit around L2. These orbits are periodic of 6 months. Operation of the spacecraft is relatively complicated business because it's operated from Mission Space Operations Center in Moscow by Lavochkin Corporation, who is responsible for ballistic and spacecraft maneuvering, spacecraft health check. But the Rosetta telescope itself is actually controlled by MPE, in the sense that we communicate to the Mission Control Center in Moscow every single commands that need to be sent. So we are the only one authorized to command Rosetta, and of course, we also are responsible for maintaining an eye on the health check of the instrument. And operation works this way: because you are at L2, you only have a window per day of communication of about 4 to 5 hours, during which we check the health of the instrument and we download the data. So we have one downloaded data per day. There are always 2 MPE members responsible for operations during each ground contact, and there is a pool of 10 people that rotates in shifts, because of course these contacts can happen during night, and they happen every single day of the year, 365 days per year. But of course, since we are also being affected by the COVID situation, and so since mid-March, we are doing most of our operation at home. So we were able to essentially shift all our mission critical software and operation scheme, and we are able to operate in this remote home. And of course, the Russians are doing the same. And despite that, I think we are continually operating without an interruption or any problem. So let me tell you something about the instrument status from the technical point of view. Essentially, here is a lot of greens, OKs. Our thermal characteristics are controlled by ITC controller, and they operate with passive cooling as expected. And so mirrors are kept within 1 degree to their operating temperature, which is about 20 degrees. The electronic cameras are kept at about -10 degrees. And the most important thing, the CCD themselves, these are the coolest point in the spacecraft, they operate at -85 degrees. This is about 5 to 10 degrees higher than what was designed originally. And we think this is due to some issues in one of the radiators, but the performance of the camera is essentially identical between -90 and -85. And all the cameras have been working fine. All the filters will have been working okay. And the camera electronics is healthy and functional. So some numbers, we have been operating with the full instrument for more than 200 days. We have now 150 days into the Optical survey, so it's almost done. It's 82% completed. And we have downloaded about 150 gigabytes of data over this time from L2 and issued thousands of commands. Let me tell you about a couple of problems that we have encountered from the beginning. One has to do with the core of the camera electronics that contains these programmable boards, FPGA are called. And these are important because do some pre-screening of the data on board before they are telemetered down. One of the things they do, for example, is to look at frames that contains MIPS, medium ionizing particles, that you essentially are due to cosmic rays that you would like to remove. And this requires to have processing power on board. However, these processing units are susceptible to single point of failure. So they could be hit by a cosmic ray themselves, which cause a bit to flip, and this causes the camera to stop working properly. The camera electronics, not the camera itself, but the electronics. And this has happened, typically it happens once per week in any of the 7 cameras. We have had, I think, 25 events like that. And we recognize that by, these are 2 examples in which we see that the image is corrupted, there are strange structure in the data that are clearly not real. And what we do in this case, we just reset the camera. And the reset is harmless. doesn't cost time. It's done in a few minutes, and the camera works fine after reset. And so we lose a fraction of the data depending on when the particle hit happened. This is a plot that showed from the start of the mission to end of April, I think, the fraction GTI, so good time interval, per each of the 7 cameras. The dark blue means 100% of the time is operating fine, and the lighter blue, that means fractional of the times are lost, and the white is when you actually switch off the camera. We had only one major scare in February where our ETC controller, so the main computer on board, also hung, and that means we had to switch off everything and on again, and we had to operate in safe mode for maybe 40 hours. That was the biggest problem we actually had. But all in all, the camera has been operating quite continuously, and so the total average GTA fraction, so good time interval fraction, from the start of the All Sky survey to a week ago is more than 96%. So we are really operating with very high efficiency, despite these small problems. Another problem we have is that 2 cameras out of 7 do not have any filter on chip, while 5 do, 2 don't. And the reason why we wanted to keep at least 2 cameras without on-chip filter is because, of course, this allows you to go to collect photons to very low energies, down to tens of electron volts, or maybe up to 100 electron volts. However, these 2 cameras, and probably all the other have, but these 2 cameras, without this protecting filter, do show some sunlight leak. Here you see in these images, the bottom corners are illuminated by very soft, this is really UV light coming from the sun, that really only contribute to events up to maybe 100 eV. You can filter them out by raising your threshold of good data. But the problem is, of course, because the sun illuminates the CCD, that change your energy and energy resolution, energy gain. So periodically, depending on the orientation of the spacecraft with the sun, you have this illumination striking in, and that will alter your energy calibration. And so it's a headache for doing, if you really want to do spectroscopy with this camera. But in terms of collecting photon and doing broadband imaging, this is really not a big problem. Couple of other calibration numbers from now in-flight calibration is our bore sight and positional accuracy. We have now enough sources detected over the sky, bright enough that can be matched to Gaia quasars, for example, and this is allow us to have a very good statistic of our positional uncertainty of point sources. And this is towards the best we could expect, of the order of 3.5 to 5 arcsecond. 1 sigma positional uncertainty. And this is now energy resolution calibrated with onboard calibration source. And so here it shows how Rosita compare a different energy with Chandra and XMM Newton. Another, of course, important point is the background. Rosita is the first X-ray mission at L2. And so here I'm showing you a plot that contains, so here a few curves. Let me go walk you through that. The blue data points with smaller bars, these are the spectrum of all the events we collect in about 4 months of All Sky survey, all the events that hit the camera, okay? So they contain particle background, cosmic background, sources, and everything. And the green line, the green data points, if you can see them, this is the spectrum of the events we get once we close the filter. This measure really the particle background, okay, in the camera. And the black and the red are a decomposition of the background measured directly into vignetted and unvignetted. So the unvignetted one should be the particle background that comes from all over sides of the camera, and the black one should be the actual cosmic X-ray background, vignetting corrected. And the solid green line here is the prediction of the particle background level we were expecting before launch. And so the first bit of bad news is that the actual level of the particle background is about a factor of 3 higher than what was predicted. The reason for that, we think, is mainly due to the fact that we are now at the very bottom of the solar cycle. And there is a clear known anti-correlation between solar cycle activity or solar wind strength with level of cosmic, cosmic ray, galactic cosmic ray induced background at L2. So we expect this to go down as the sun starts become active again. The good and part of the other part of the discrepancy is that the modeling we did of the instrument maybe was not so accurate. The good news, however, is that this background is very stable. Here you see the filter wheel closed measurements, so the particle background level of uncertainty, the flux distribution, which has the maximum balance of 6%. And this is an even better illustration. This is actually a simultaneous observation of the variable AGN, 1H2707 for the AGN aficionados. The top panel is the Rosita soft point light curve. But what I really want to point out to you is the solid lines in the bottom, which is the background measured by Rosita in different energy bands. And this is simultaneous observation with XMM Newton, the PN and MOS. And here you see how much more variable the XMM background light curves are compared to the Rosita one. Okay, I think this is about it, what I want to tell you about technical operational characteristics. So in the last 15 minutes or so, 20 minutes maybe, I think finally I can relax and show you some pretty pictures and early results. So this, you might have seen it before. This is our first light images. We pointed at the LMC as it is tradition for X-ray instruments. These are the 7 camera individual images one by one. You may notice that the orientation of each camera with respect to the sky is different. And this, of course, is done on purpose so that our readout strikes are always oriented differently when we scan the sky. You see now the 7 camera image combined of the LMC. The pointing was centered on supernova 1987A, which is this very bright source at the center. But here you can see, of course, in this false color image taken between 0.2 and 4.5 keV, all sorts of different interesting diffuse emission of different temperatures and many background and foreground point sources, which are either compact object in the LMC or, of course, more numerous background AGN, or some cases foreground stars in the Milky Way. And here there is a bright X-ray source LMCX1, which itself was just outside our field of view, this circular field of view, but because it's so bright, it creates stray light from single reflection that you can clearly see here. So image artifacts. And this is as a comparison now, in the center, you see now blinking between the two, the XMM first light image also pointed on the LMC, but of course with similar, slightly better spatial resolution, but similar sensitivity, but a much smaller field of view. The source itself, this is, I think it's an 80 kilosecond exposure. And so we have very good spectrum for the central supernova 1987A. And this plot shows the Rosita spectrum in cyan compared to the XMM Newton spectrum for a slightly shorter exposure. But the main reason why I'm showing this is not to talk about the cross calibration between Rosita XMM that we are still working on, but to show how sharper the advantage of the better spectral resolution of Rosita, how sharper the different metal lines are in the Rosita spectrum. And this is another of our first light package images. Well, this is not the Rosita image. This is a ROSAT image of a system, a triple system of interacting clusters of galaxies, Abell 3391, 3395. There is a northern cluster and the actual couple of southern clusters with some enhanced emission in between. XMM has pointed at this system with 3 separate pointings, one center on the top cluster, one center on the bottom system, and one center in the middle where there is a group, and there is a lot of interesting stuff to be studied about the stripped hot material from this interacting cluster system. So, of course, with the Rosita, we have this raster scan option that I told you before, so we can cover this entire 2 by 2 or so 2.5 by 2.5 square degree field with this, and this is actually the Rosita image. With simple Gaussian smoothing. So every source you see here is an X-ray source, and this you can see the clusters and the plethora of background AGN. What is interesting in the Rosita image, of course, is not just how beautiful that is, but also that it contains clearly extended sources a number of which are actually at the same redshift of this interacting cluster. So we are exploring the large-scale structure around this and start finding infalling clumps and groups. That's the same system, same data set, different rendition of the data. On the left, it's a false color image, so you can appreciate the difference in the background AGN spectral by looking at different colors. We have hard and soft sources. And here on the right is a single energy image, but with wavelet filtered, so to enhance the diffuse emission from the stripped gas in the bridge region. This is another nice story. This is, again, an older image of a supernova remnants, Puppis A. And this was done at MPE by a rocket flight in February 79. So 40 years before the launch of eROSITA or more. And this was actually the first time soft X-ray photons were collected at different energy. So you can do a color image, and actually was one of the first time you can use a color screen in your office to look at astronomical images. And so we have revisited Puppis A with eROSITA after 40 years. And that's the eROSITA image. It's also a bit more than 1 degree wide, maybe 50, 60 kilosecond exposure. But you show the beauty now of having the enhanced energy, spectral, and spatial resolution. A few more highlights of our calibration program. We have now working hard on accurately calibrating vignetting an effective area. To do so, we use clusters, for example. These are 2 clusters, a very relaxed one on the left and a merging cluster on the right that were exposed by maybe 50, 60 kilosecond. And we can study in greater detail the cluster emission profiles, studying the background and the vignetting property of the telescope. The same cluster on the right is now shown to enhance the very nice structure in the IC. And we know this is a merging cluster. You can see bubbles. You really see a lot of details. The one on the left is a coma, another merging cluster, a very famous one. This is an even zoomed out view, maybe 3 by 3 square degrees, I don't remember. So it's quite a deep exposure that shows a lot of foreground and background objects. We spent most of the time during November doing calibration observation and performance verification. So we have a big program of early science we are working on. The largest investment of time was spent on a mini survey that is called IFEDS that I'm showing here. And the idea of IFEDS was to go over a large enough area, in this case is about 140 square degrees, to the depth that eROSITA will reach over the whole sky at the end of the whole sky survey in 4 years' time. So kind of giving a preview of what the X-ray sky will look like after eROSITA. And so we exposed this 140 square degree to 2.5 kilosecond on average. And what I'm showing here is an exposure corrected image of the 0.5 to 2 kV band. Almost by eye, you can see that there are clearly extended sources. So our pipeline recognized more than 400 X-ray extended sources that we associate to clusters of galaxies. And using the optical data, this is a gamma equatorial field. It's known for having a lot of good multi-wavelength optical data and infrared data. So we can do immediately photometric redshift identification of these clusters, and we have confirmed maybe 350 over the area where the optical images are there, with a few extending up to redshift 1. So this is a very basic plot that shows the luminosity versus redshift of these clusters. And this blue curve is a very Pullman flux limit. Of course, cluster detection is not simply flux limited, but this illustrates how close we are to the expected performance in terms of sensitivity to clusters. And because we have very good Subaru data, imaging data that can be used to do lensing, we have started looking at the lensing mass of these clusters. So we have now 365 X-ray detected clusters for which we have lensing mass that will be very important to calibrate the mass measurement for these clusters. It's very preliminary work, but it shows again how this is a function of 1 plus z. So there are clusters, a few clusters confirmed at redshift higher than 1, which is important because they contain a lot of information about cosmology for what I was telling you at the beginning. And this is a comparison of the location of this cluster in the mass redshift plane Unfortunately, I don't have a log1+z version of it, but it shows the expected location of the Rosita pre-launch compared to the actual location of the Rosita cluster. So that's also quite a good confirmation of our performance of the instrument. And this is one zoom in one relatively high redshift but bright cluster, massive one, 7 times 10 to the 14th solar mass, redshift 0.57. This is the R500, and this essentially to show you that we can clearly resolve the cluster surface brightness profile, at least in the brighter fraction of the clusters. So here you see the profile compared to the PSF in blue and the nominal background level in green. And then that means we can do ICM studies. This is now the spectrum of the same cluster on the right, flux as a function of energy, that we use to determine the temperature to maybe 20–30%, 1 sigma uncertainty for this object. And this is another example of what one can do once you have clusters over that large an area. You can study superclusters, or at least a cluster that happens to be associated to optical density map. So the X-ray cluster are on the left and the HSC galaxy density map on the right, filtered with some photometric redshift. So this is a structure redshift 0.35 that we are seeing aligning more or less along filaments. And so we can probe this on scales of tens of megaparsec with our data. Okay, let me go back to the image. The image, of course, does not contain only 400 sources. In fact, contain more than 25,000 point source detected. And by just sheer number, this Rosita PV phase mini survey experiment is already the largest contiguous X-ray survey ever done. We chose a field because we knew there was already a lot of spectroscopy there. We have supplemented it with our own SDSS4 program called SPIDER. So we are now have, for this object, almost 6,000 redshift already. So it's already reached X-ray survey field to harvest. We are looking at the optical X-ray distribution of our objects. Here you see that the optical magnitude of the counterparts of the AGN, as expected from pre-launch activity, typically peak at 21st magnitude. And here black and red separates objects that have proper motion in Gaia, the red ones, from the ones that don't. So you clearly see where X-ray stars are compared to X-ray AGN. And so I told you we have spectroscopic redshift for many sources. This is a compilation of type 1 quasars. We have already detected almost 4,000 type 1 quasars in this IFETS field with spectroscopic redshift. This is a comparison of the redshift luminosity distribution of them compared to the Rosat quasars in blue. And among these, we have rediscovered the already known high redshift quasar at redshift 5.8. The reason why I'm mentioning this is however, is the first time a redshift, almost redshift 6 quasar is discovered in a blind X-ray survey field, so it's not followed up. So it's the highest redshift X-ray blind detection. And we have a number of candidates from colors. This is typical colors track for high redshift objects, and the gray squares represent the colors of candidates redshift 4.5 or higher quasar. We have 35 candidates, out of which there are maybe 4 or 5 which have very good photometry in multiband that suggest redshift 5 or so photometric redshift. I think this is probably the most promising candidate with the redshift 4.5 photometric redshift. We are trying to get spectroscopy for those. And as I told you, there are about 15% of stars in the IFETS field. This on the left is the Hertzsprung-Russell diagram of the X-ray detected stars. Bolometric luminosity, magnitude versus Gaia colors. That's the main sequence, and these are all color-coded by the X-ray luminosity. And this is now the same stars, same color on the x-axis, but X-ray to bolometric luminosity ratio for these stars. That tells you something about their probably their rotation rate or their youth. So it's an interesting study to be carried out. Okay, I think now I'm closing in to tell you with a couple of slides about where we are doing. The Old Sky survey image is here, or if you want, what I'm showing here now is the status of this Old Sky survey projected into the sky as of 2-3 weeks ago. And zooming in on some of the nicer structure, we appreciate the advantage of the unlimited field of view that you get by serving the sky with uniform sensitivity. So here, for example, is an extragalactic patch of the sky of a few square degrees, where you see, this is the famous Shapley supercluster, but you can clearly see the nice uniform image quality. This is now a beautiful supernova remnants. Again, we are looking at object on scales of degrees, which will be harder to study in detail if you had a smaller field of view. And this is now a galactic plane zoom in, where you see another beautiful supernova remnants, and this even more spectacular circle, which is a echo of X-ray binary outburst scattered by the dust along the line of sight. So it's so-called dust scattering halo. And there are actually a number of circles. We can use them to study the distribution of dust along the line of sight. This is now a preview of the simple, I'm projecting the X-ray photons from Rosita, smoothing them by a few pixels, and projecting them on the sky. The galactic center is here on the left, 0, 0. And I'm showing you in a minute an overview of about 1/4 of the galactic plane in X-rays. This is the most sensitive Rosita band between 0.6 and 2.3 keV. And you see, of course, many bright sources, many nice supernova remnants, a lot of diffuse emission structure, and this in the end is this bright diffuse thing in the end is the Eta Carinae nebula. So one word about transients. I told you we are scanning the sky continuously. We're getting data telemetry once per day, and these data are fed to our standard processing that creates image and detects sources and creates catalogs. But at the same time, the same data go through a near real-time analysis software that was built mainly to do housekeeping parameter check and health check of the instrument. But we can use this to detect very bright sources immediately, a few seconds after they enter our telemetry stream. And the combination of these two streams allow us to right now trigger an internal mechanism that alerts us when there are new X-ray sources, for example, by comparing with the Rosatol Sky Survey or with past Swift, XMM, and Chandra images. And right now we are doing an internal vetting of this data, but in the future we are issuing ATELs for the most interesting ones. And in the future, we think over 1 year time, we will be able to move to a more automatic system of sending alerts to the community faster. This is just a list of a few alerts. We are getting more and more over the last few days. So the latest one at the top, they contain different kind of sources, galactic transients, bright unknown transients in blue, extragalactic transients. The latest one of just last week is super interesting. This is a bright nuclear source in this nearby galaxy that Rosita's caught at a flux level 90 times larger than the previous XMM observation. So a huge flare. The X-ray spectrum is very soft, and the optical light curve is very peculiar. There was a very bright flare 1 year ago that went down by 3 magnitude, and then we caught it again into this rebrightening. And we actually don't know what this source is. It's very exciting. We are getting follow-up time now with Swift. Okay, summary slide about the Sky Survey, and then I'm done. More than 80% of the sky have been covered. We have collected, I think we counted over the order of 300 million calibrated photons in the energy range between 0.1 and 5 keV. The sky has been exposed uniformly now, about 200 second exposure in every point, with larger exposure towards the ecliptic pole. And because the background is very stable, there are essentially no background flares that we have seen during the Sky Survey. And because of our flexible mission planning, even when we have troubles with the cameras, as it happened in February, we can go back and fill the gap. So we are covering the sky without gaps so far. So hopefully we'll have nice press release image next month. We have discovered numerous transients, and we are now fine-tuning the vetting mechanism to follow up them. And we have already done some preliminary source detection over the sky. More than 350,000 sources have already been detected in the hemisphere we are analyzing in Germany. And so this means we are very well on track to discover within a few months more new X-ray sources with Rosita than all previous X-ray missions in 60 years have cataloged, which are about 1.2 million. This is my final summary slide. This is everything I told you. We had a successful launch last July. Our instrument performance has been confirmed by the very good image quality, spectral resolution, and high observing efficiency. So all our prediction from before the survey look good in terms of the number of objects we will be able to detect. We have some issues. The most annoying one is this optical light leak in these two telescopes that degrades the soft spectral resolution. And small data loss due to the unstable behavior of the detector electronic. And of course, the higher particle background reduce our sensitivity in the hard band above 2.5 kV or so. The data have been collected. The PV phase, including FEDs and the calibration data, will be released early next year, so 1 year after the completion of the calibration program. And the survey data, as I told you, for the German part, will be also released after a proprietary period of 2 years, so in 2022, 24, and 26. And after that, as I said, we opening up the telescope for usage by the whole community. That's it. Thank you, of course, and this also a chance for me again to thank the many people that have worked over the years on the project and on the mission, and just this is a way to credit all or at least most of them. Thank you.